So we'll learn a different thing known as solid angle. So by angle we know about plane angle, right? So what's a plane angle? It seems quite obvious that plane angle. Okay, I know what 30 degrees is, right? 30 degree means this, 30 degree means this, 90 degree means this, 45 degree means this. Okay, so how do you define plane angle? Say if you take a circle and this is the center of the circle O, and you consider an arc like this, and say the length of the arc is S and the radius of the arc is R, and the plane angle, then the plane angle theta subtended by the arc at the center of the circle is given by theta is equal to S divided by R and the unit of this angle is radians, RAD. But to draw an angle, see, every time there is no need to draw a circle, right? So this is 30 degree angle, right? This is 30 degree, this is 90 degree, and 90 degree means in radians that will be pi by 2 radian, pi by 2 radian, and this is 45 degree, this is pi by 4 radian, and this is pi by 6 radian. Okay, so if it is 90 degree, if it is pi by 2 radian, that means this, right? If you measure this length of the arc S divided by this, so this in for this case the S divided by the ray, so the length of the arc S divided by the radius of the arc S will be equal to pi by 2, and this S equal to pi r divided by 2, and that we know, that's true. Okay, now we'll learn a different type of angle known as solid angle. Solid angle, and the unit of solid angle is written like this, SR, and the unit is steradian. And the solid angle is a three-dimensional angle, that is a three-dimensional angle, and it's like this. It's a three-dimensional angle. This one, right? I mean this cone, I mean this cone like thing, right? So if you have an ice cream cone, suppose you have an ice cream cone like this, and your friend has an ice cream cone like this, and there lies this ice cream, there lies his ice cream, your friend's, it has got more solid angle. The solid angle is more than this, I mean this three-dimensional angle. Now I will define solid angle. So more solid angle means more volume of this ice cream. That's all. So this is also defined in terms of sphere. So let's see this. Say there is a sphere like this. This is the center of the sphere O, and say consider an onion or a tomato, and you are chopping it on a board, a chopping board. So in same way we'll pass through a chopping board, a chopping knife. There it goes. This is the chopping knife. This onion of spherical shape is chopped through like this, and this, so there is a surface area here, this spherical surface. See, I am talking about this area of the surface, this much area of the surface, this area A, A on the surface of the sphere, and it will subtend a three-dimensional angle denoted by omega. This omega steradian, right, is the solid angle. Now this omega solid angle is defined like, as suppose the radius of the sphere is r, this omega is defined as this area divided by square of the radius. See, it's dimensionally correct also, because the surface area obviously it has dimensions of what, the square of the length. So if you divide the surface area by the square of the radius, you get a dimensionless quantity. So that's the solid angle. Okay, now we will find out this solid angle. Right, now this finding out this solid angle will be in terms of this. I'll use one more page for this. Suppose there is a sphere, this is the center. Now that's the chopping knife, spherical onion, and this is the plane angle. This is the, or rather it is the, I mean these lines will be like the slant surfaces of the cone, and this theta appears to be like the semi vertical angle of the cone. Okay, now in terms of this theta we will find out this area A. Okay, now take any angle phi here, and with phi, you know, d phi will be following phi, this small angle d phi. So what about this length? This small length is equal to r times d phi. Now here we get these rings again, so I have to make one more diagram for it, maybe many more, one won't be sufficient. So that's phi, that's d phi. See, look at this, this is a ring, okay. Now this small length is equal to r times d phi, and what about the radius of the ring? The radius of the ring is r sin phi. So the area of this ring, so area of the ring is equal to 2 pi r sin phi multiplied by r d phi. So area of a ring is its circumference multiplied by the thickness. Thickness is r d phi and the circumference is 2 pi r sin phi. Now we have to find out this total area, as in this diagram. Say you have to find out this much total area, right? So you have to integrate over the rings and do it in this page. So that total area is equal to integration of, say, 2 pi r sin phi into r d phi. So integration of 2 pi r square 2 pi r square sin phi times d phi. Now the limit of phi will be from 0 to theta. So here it is, so equal to 2 pi r square integral sin phi d phi, we get cos phi minus cos phi rather, so 0 to theta. Just you can swap the limits, so cos phi theta to 0, so that's 2 pi r square times 1 minus cos phi, sorry, beg your pardon, it's cos theta, 2 pi r square 1 minus cos theta. This is the area. cos theta. So the solid angle equal to 2 pi times 1 minus cos theta. So that is a relation between the plane angle and the solid angle. Now the solid angle, suppose for example this that's a sphere. So suppose this makes angle 60 degree. So you have to find out this much area A. So what will be this much area A? Already we know it's 2 pi r square 1 minus cos of 60, that is equal to pi r square. A is equal to pi r square, and the solid angle is equal to, you can use that formula, 2 pi into 1 minus cos of 60. So this solid angle subtended here is equal to pi is teradian, right? Okay, so that's the concept of solid angle, right? Now so the total solid angle subtended in space, what will be its value? Total solid angle of space around a point. So this is equal to, obviously it will the total surface of the sphere. How much it is? Total surface of the surface area of the sphere, 4 pi r square by r square. So that's 4 pi steradian. So the net solid angle is 4 pi steradian, right? So this is a very very helpful concept, solid angle. So just an example I'll show you. So suppose in a problem there is a point source of light, though this is a point source of light of power is equal to P, capital P here, and say at a distance x you have a disk. So you have a disk, it's like a black body, so it will absorb all the power. It has radius r. Okay, so find the energy absorbed, by the disk in 1 second. That means we have to find out the fraction of the power. So that's a black body, obviously, it won't reflect anything, absorbed all the power. So if you see this, the light in energy from the point source will go in all directions, equally in all directions, right? And some portion of it will be absorbed by the disk kept at a distance x. So here you see this problem I will solve by the concept of solid angle in the following way. See, so the energy absorbed by the disk depends on the solid angle omega subtended by the disk here. So this will be theta each. So the energy absorbed in 1 second by the disk, that we can write that this power, total power, divided by 4 pi solid angle. That means the whole solid angle of space. So P divided by 4 pi multiplied by the solid angle subtended by the disk at the point source. So here you get P by 4 pi into solid angle is 2 pi 1 minus cos of theta, and cos of theta is x by square root of r square plus x square. Okay. Now suppose there is a point charge q. Suppose there is a point charge q, and at a distance r from the point charge, you have an area dA. This is an area dA, and the vector dA is this way. Obviously, the vector area will be perpendicular to the surface dA. Okay. Now there it is, this is the vector r cap, right? This is the vector r cap. Now let this be theta. Now this r cap, it is same as the direction of the electric field at this point due to this point charge q. Now, so we have to find the flux through dA, due to the charge q only. So that is flux through dA d phi is equal to E dot dA, right? Now so E dot dA means E is q by 4 pi epsilon naught r square into r cap times so dot dA. Okay, so that is d phi is equal to q by 4 pi epsilon naught that's equal to 4 pi epsilon naught r square multiplied by dA cos theta, right? Now what is dA cos theta actually? See, dA cos theta is this area, right? The component of this area, see, this is also theta, so this component of the area is dA cos theta, and the solid angle subtended by this dA at q, or this dA cos theta at q, same thing, is this much. This is omega, or say d omega, the small solid angle. So d omega is obviously equal to dA cos theta by r square, because it depends on the perpendicular component of the area. It depends on the perpendicular area, right? So I think you got this, right? This dA, the component of this area, is dA cos theta. So the solid angle is obviously dA cos theta. Suppose you have a sphere, say you consider a portion of the sphere. That is how you have defined solid angle, right? So if you consider a portion of the sphere, small area, by this square of this radius, this will be a small solid angle. Obviously this small area, or the small surface of the sphere, will be perpendicular to this r, or the vector area will be parallel to this r. Okay, right. So d omega is equal to dA cos theta by r square. So you can rewrite this d phi as d phi is equal to how much it was, q by 4 pi epsilon naught r square into dA cos theta. Now this dA cos theta by r square is d omega, so q by 4 pi epsilon naught d omega. So now I'll consider a closed surface. Now there it was, right, dA, whatever, this was the dA. Okay, now this was the small solid angle d omega subtended by dA. Now the total flux the net flux through the closed surface is equal to how much? Phi equal to, so it will be summation of this, so it will be summation of d phi. So you have to sum over these solid angles, right? So q by 4 pi epsilon naught summation of integral, closed integral of d omega. So what will you get? Closed integral of this small solid angle. Obviously the total solid angle in space you get 4 pi. So q by epsilon naught due to this point charge. Okay, similarly we can show that whatever, so whatever number of point charges there may be, the total flux is equal to sigma of q inside by epsilon naught. And again I tell you that Gauss's law is independent of the medium, right? In medium there are bound charges, so it appears like that the Gauss's law does not hold in medium. That we will discuss later. In our next lecture we will discuss properties of conductors.